Welcome to True Projects. In this video, we are going to explain the project entitled as Enhancing Malaria Detection Through Deep Learning, a comparative study of convolutional neural networks. So before getting into the video, let me give you the brief description about the project. This study explores the use of deep learning techniques to improve malaria detection from microscopic blood stream images. It compares the performance of different convolutional neural network architectures in accurately identifying malaria infected cells. The research evaluates models based on accuracy, sensitivity, and computational efficiency to determine the most effective approach. The finding highlights the potential of CNN based systems as a reliable tool for early and automated malaria diagnosis. Coming to the abstract, this abstract explains the motivation, approach, and significance of the project on malaria detection. It highlights the global impact of malaria and the limitations of traditional manual diagnostic methods, such as being time consuming and error prone. The abstract then introduces deep learning, particularly convolutional neural networks, as an effective solution for medical image analysis. It describes how multiple CNN models are trained and compared to classify infected and uninfected red blood cells using standard evaluation metrics. Finally, it emphasized that the improved accuracy and efficiency of CNN based systems make them a reliable and practical opinion for automated malaria diagnosis, especially in source limited settings. Coming to the existing system, the existing malaria detection system relies mainly on manual and semi automated methods that have several limitations. Microscopic examinations of blood smear slides requires skilled technicians and it is time consuming with accuracy heavily influenced by human experts, fatigue, and subjective judgment. Rapid diagnosis test offers faster results but often fails to detect low levels of parasites and cannot measure parasite density. Although traditional machine learning techniques have been applied using manual extracted image features, they involve complex feature engineering and struggles with intricate visual patterns. As a result, these conventional approaches provide limited accuracy and efficiency compared to advanced deep learning based methods. Coming to the proposed system or base paper work, the proposed system introduces an automated malaria detection approach using convolutional neural networks. The proposed system introduces an automated malaria detection approach using convolutional neural networks to overcome the limitations of traditional diagnostic methods. By directly learning relevant features from microscopic blood smear images, CNN removes the need for manual feature extraction and reduce human involvement in diagnostic process. The system compares multiple CNN architectures to determine the most accurate and efficient model for classifying infected and uninfected red blood cells. Model performance is assessed using standard evaluation metrics along with computational efficiency to ensure practical usability. Overall, this approach delivers faster, more accurate, and scalable malaria diagnosis, making it especially valuable for healthcare environments with limited resources. Coming to the dataset, the cell images for detecting malaria dataset from Kaggle is a widely used and reliable resource for developing automated malaria detection systems. It consists of a large number of microscopic red blood cell images that are clearly labeled as either parasites or uninfected, making it deal for binary classification task. Captured through light microscopy, the images can be easily pre-processed and resized to suit deep learning models, particularly convolutional neural networks. Due to its size, quality, and accurate labeling, this dataset supports effective model training, testing, and performance evaluation, contributing to robust and accurate malaria detection research. Coming to the novelty or extension or enhancement or improvement. As an extension to the base CNN model, advanced architectures such as exception and the hybrid density based model were implemented to improve feature extraction and classification performance. By combining the strengths of two models, the hybrid approach captures both deep and fine grained features, leading to better accuracy and robustness in detecting malaria infected cells. The YOLO family was utilized to detect abnormalities directly within blood smear images. Unlike classification models, YOLO performs real time object detection, enabling the system to localize infected regions within images. This extension enhances the system's capability by not only identifying infection but also visually pinpointing abnormal areas. Furthermore, to improve model transparency, a trust the explainable AI techniques GradCam was applied. GradCam generates heat maps that highlights the most influential regions of an image used by model for prediction. This helps user and medical professionals understand the decision making process of deep learning models and validates whether the model focuses on relevant biological features. In addition, a user friendly interface was developed using Flask Web Framework to make the system accessible and easy to use. The interface allows users to upload blood smear images and receive real time predictions from the trained models. This extension bridges the gap between technical implementation and practical deployment, enabling smooth interaction for non technical users. Coming to the flow of the work, first, we need to import the packages. All required Python libraries and frameworks such as TensorFlow, PyTorch, TorchVision, OpenCV, YOLO, and Flask are imported. These packages support data handling and model training evaluation and web deployment. Next, dataset preparation. The malaria cell image dataset is collected and organized into two classes, infected and uninfected. One redundant cell image folder containing 27,000 images is manually removed to avoid duplication and imbalance. Next, pre-processing. For classification, images are augmented through resizing to 299 into 292, random horizontal flipping, rotation, and tensor conversation to improve model generalization. For detection, multiple datasets are merged and a data.yml file is created to define image paths and class labels for YOLO training. Next, maintain parallel datasets. Two parallel datasets are maintained to support different tasks. Classification uses image label pairs, while YOLO detection uses images with corresponding bounding box annotations. Next, model training. Multiple classification models ranging from baseline CNNs to advanced architectures like VGG16, Exception DenseNet 201, and ensemble models are trained and compared. YOLO versions are trained for object detection, and all models are evaluated using appropriate performance metrics. Next, model evaluation. Classification models are evaluated using accuracy, precision, recall, FN score, confusion matrix, specificity, sensitivity, error rate, and ROC curve. YOLO models are evaluated using MAP, precision, recall. Next, interface pipeline. The interface pipeline accepts an input image and processes it through trained models. The output includes detected bounding boxes with class labels and the predicted malaria type. Next, Flask web application. The Flask based web application is developed with an HTML frontend for image uploads. The backend first performs YOLO based detection, followed by classification, and then displays results with bounding boxes, predicted classes, and confidence score. The algorithms used are for classification model, we have used baseline CNN models like CNN with ReLU, CNN with leaky ReLU, CNN with data augmentation plus ReLU, VGG16, and extension models we have used Exception, DenseNet 201, and Ensemble, which consists of Exception plus DenseNet. And as an extension for YOLO based detection models, we have used YOLO V5, YOLO V8, YOLO V9, and YOLO V11. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consisting of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consisting of application framework Anaconda, primary language Python, front-end framework Flask, backend is Jupyter Notebook, database is SQLite 3. Technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap 4. To execute the project first, we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. Models. These are the model files which contain algorithm information which will be loaded into the project code during the runtime. IPYNB files. These are the Jupyter Notebook files which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Now, coming to the execution of the project, first you need to copy the path of the code folder from the address bar of the file explorer. Then open Anaconda prompt. Use the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it in any web browser. I prefer Chrome. The home page of the project should now be displayed in the browser. This is a front-end build using Flask framework. In this page, we have home button and register button. Firstly, click on register button so that the create account form will be open, where you need to enter the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. And once again, reconfirm your password. Then click on create an account so that all the given details are stored in signup.db and login.html will be opened, where you need to access the application with the help of your username and your password. Then click on sign in so that the prediction page has been displayed. In this page, we have home button, predictions button, data analysis button, notebooks button, and sign out button. Firstly, click on predictions button. As we are dealing with classification and detection, both the things are being opened. Let us check one by one. First, click on classification button so that the image classification form will be opened, where you need to upload your blood smear image and then detect. So firstly, click on choose file and you can input your image. The image has been successfully uploaded, and click on classify image so that the given image is pre-processed and the output will be displayed as the given image is detected as parasitist and the confidence level is of 100%. This is the original image which we have uploaded, and this is the analysis result. And classification probability for parasitis, it's 100%. Malaria parasitis has been detected. Immediate actions what we need to take is given below, and we also have the precautions and safety measures. Then click on upload another image so that the image form will be displayed, where you can upload another image. The other image has been successfully uploaded. Click on classify image so that the given image is pre-processed and the output will be displayed as uninfected, which means the given image is uninfected and the confidence score is of 100%. This is the original image and this is the analysis result image. And we have the classification probabilities like it is uninfected. The confidence score is of 100%, which means no malaria parasitis is detected. And here we have the recommendations, preventive measures and health tips. Now click on prediction button again and let us check with YOLO detection. When you click on this YOLO detection button, the form will be opened where you need to upload the blood smear images, choose file and upload the image. The image has been successfully uploaded and click on run YOLO detection so that the given image is pre-processed and the output will be displayed as YOLO detection completed, which means detection results with bounding boxes. Not infected and infected. It's been clearly given with the help of blue color bounding boxes. And here we have understanding YOLO detection results like bounding boxes, real-time processing, confidence score, and object localization. And we also have the detection process and detection features. Now click on data analysis so that the graphical representation of classification and detection will be open. Let us check one by one, first with classification. In this, we have the performance metrics and visualizations like accuracy, precision, recall, and F1 score results, along with the graphical representations. In this, we have first the confusion matrix graph. This confusion matrix shows the model's classification performance for parasitist versus uninfected cases. It correctly classifies 2,698 parasitists and 2,701 5 uninfected samples with only 61 false negatives and 38 false positives. Overall, the high diagonal values indicating strong accuracy and reliable predictions. Next, we have ROC curve graph. The ROC curve shows that the trade-off between the true positive rates and false positive rate across different thresholds. An AUC of 0.997 indicates excellent model performance, meaning the classifier can almost perfectly distinguish between the two classes. Next, we have training versus validation loss graph. The training loss steadily decreases, showing the model is learning well on the training data. However, the validation loss increases the fluctuates, indicating possible overfitting as model does not generalize as well to unseen data. Next, we have training versus validation accuracy. The training accuracy steadily increases and approaches 99.8%, showing the model is learning the training data very well over epochs. Validation accuracy fluctuates around 97.5% to 98.3% without a clear upward trend, suggesting the model may be slightly overfitting and not improving generalization as much. Next, we have accuracy by model graph. The bar chart compares accuracy across different models, showing a steadily improvement from a baseline to advanced architectures. Exception, DenseNet, and the ensemble model achieve the highest accuracy, indicating that deeper and combined models provide better performance than simpler ones. Next, we have precision by model graph. The bar chart shows precision scores for different ML models, with all models achieving higher precision above 95%. Advanced architectures like exception, DenseNet, and ensemble model perform best, indicating fewer false positive compared to simpler models. Next, we have recall by model graph. The bar chart compares recall scores across different ML models. Recall steadily improves from the baseline through the advanced deep learning models, with exception, DenseNet, and the ensemble achieving the highest recall. Next, we have F1 score by model graph. The graph shows the F1 scores performance of different ML models. Advanced architectures and the ensemble model achieve the highest F1 score, indicating a better balance between precision and recall compared to the baselines and simpler models. Next, we have specificity by model graph. The bar chart compares the specificity of different ML models. Specificity increases consistently from the baseline to the advanced models, with exception, DenseNet, and the ensemble showing the best ability to correctly identify negative cases. Next, we have sensitivity by model graph. The bar chart compares sensitivity across different ML models, showing that all model performance varies strongly. Advanced architectures like VGG16, exception, and the ensemble slightly outperforms the baseline, and simpler models indicating better ability to correctly identify positive cases. Next, we have error by model graph. The graph shows the error rates for different ML models, with advanced models generally producing fewer errors than the baseline. Exception and the ensemble model achieves the lowest error rates, indicating more accurate and reliable predictions compared to simpler models. And now let us check with YOLO detection graphs. In this first we have YOLO precision graph. The chart compares precision across YOLO versions, showing that YOLO V9 achieves the highest precision, meaning fewer false positives. YOLO V5 and YOLO V8 perform similarly with strong precision, while YOLO V11 shows a slightly lower but still competitive performance. Next, we have YOLO recall graph. The graph compares recall across different YOLO versions. YOLO V9 shows the highest recall, closely followed by YOLO V5 and YOLO V8, indicating strong detection performance. YOLO V11 has noticeably lower recall, meaning it misses more true objects compared to the others. Next, we have YOLO MAP graph. The graph shows the mean average precision for different YOLO models. YOLO V9 achieves the highest MAP, indicating the best overall detection accuracy, with YOLO V5 and YOLO V8 very close behind. YOLO V11 performs comparatively lower, suggesting weaker precision recall balance. And then click on Sign Out. So finally, this study shows that deep learning, especially convolutional neural network, can significantly improve the accuracy and the speed of malaria detection from microscopic blood smear images. The comparative analysis indicates that optimized CNN models outperform traditional diagnostic methods and basic machine learning approaches. Such automated systems can support healthcare professionals in early and reliable diagnosis. Overall, deep learning based detection has strong potential to enhance malaria screening, particularly in resource limited settings. This is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.